Hi, my name's Steve Kendricks. I am the Senior Technical Product Manager for AWS Batch. We're here today to talk about something near and dear to my heart, which is machine learning on AWS and particularly AWS Batch. Something that we like to do is bring in customers to talk about what they're doing with our platforms, right? And so today we have Ali Gale and Matt Smith to discuss machine learning at Lyft and how they leverage AWS platforms, particularly AWS Batch and Amazon EKS in order to do that. We're also going to talk about an exciting workflow manager that the Lyft team has built on top of us and have open source called Flight. And we'll talk about how it works and what you can do with it today. I am going to give you a brief overview into Batch. I'm not going to go too much into details about how it works. There's plenty of other videos, especially coming out of 2019 reInvent, that you should take a look at to kind of get into the weeds about how Batch works and some of the other use cases that we have. I'm just going to give you a brief overview of some of the high-level concepts about AWS Batch and who uses it so that you have an idea of how it works. And I will let Ali and Matt take over when it comes time to talking about how Flight does it and what Lyft uses it for today. So I am going to give you, let's talk about Batch and an intro to some of its basic concepts, right? So we built AWS Batch as kind of a way to have scheduling native in the cloud, right? What do I mean by that? Well, a lot of on-premise schedulers such as Slurm, which you might be familiar with, are built kind of with the concept of on-premise scheduling, right? It has an idea of a fixed concept of a cluster. It has an idea of what compute resources are there, and it knows in order to make decisions about where to run jobs and work. With the cloud, we have a little bit more concept of breadth in terms of a wide variety of compute resources and file systems, and we also have depth, right, and scale, and most importantly, that scale is elastic, right? So with Batch, we built a cloud-native scheduler that helps take advantage of the breadth and the depth and the elasticity of the cloud, right, and all so that you can focus on your work. So it is fully managed. It's something that we manage the compute for you, we manage the resources and the instance lifecycle. We manage choosing instances for you, right? If you have a particular instance family that you like to work with, you can do that. However, Batch will also give you the flexibility to just say, I only want to care about my work and the resources that my work required, and I will let Batch take care of the rest. Batch is fully integrated with AWS services, right? So if we think about all of the breadth of AWS services, you need kind of integration with those, especially with file systems, new instance families as they release, step functions, auto scaling, and those sorts of integration. Batch takes care of handles for those, and we're constantly getting better as new services and as new compute and file systems release, right? We will integrate with those to give you the maximum leverage when using cloud resources. Batch is also optimized for resource provisioning. What we mean by that is that we take care of handling instance provisioning for you, right, in an optimized way, right? So we will take a look at your workflow, we'll take a look at the work that you need to get done, and we will scale up instances accordingly, right? And we'll always try and give you the lowest cost. We'll try to maximize your resource use. We are also integrated with the spot market, right? And so if you want to take advantage of 70, 80% on your compute costs, right, you can then use Batch to leverage the spot market. And there's a couple of very good videos coming out of reInvent this year to discuss how Batch does that more technically. Who uses AWS Batch, right? We have a couple of major use cases, but generally, right, we're going to talk about machine learning today in some aspects, but we have a wide variety of customers using Batch, from autonomous vehicles, machine learning, simulations, for example, healthcare and life sciences, weather systems, forecasting, modeling, financial risk analytics, and many, many more, right? Image transformation is a very common one. We have a wide variety of use cases. Again, any sort of asynchronous work of somewhat moderate to long duration times are what we consider target jobs for AWS Batch. Just to give you a brief overview of how AWS Batch works, right? So let's take the example of an image transformation, right? What the customer does is they provide us with the job definition. This is your application image and your configuration and your IAM role and permissions. What happens then is very often, right, customers will, in the role of image transformation, new images, right, new input will arrive in the customer's account, probably in the form of an S3 bucket. What happens then is that that triggers an event, and that then submits jobs to an AWS Batch job queue, right? So you've already set up this job queue ahead of time. It is managed in Batch, it's stored in Batch, right? You don't need to worry about it. We take care of it for you. When the jobs arrive, we will evaluate them in approximately FIFO order. And what that means essentially, as jobs are submitted, we will then process them. We will begin spinning up instances in a AWS Batch compute environment for those jobs. So we maintain a holistic view of the queue. We will evaluate what jobs are needed, what instances are needed to run the workload in the queue, right? We will pick an optimal mix if you want, or we will kind of, launch the instances that you request us to provision, right? You can also control the compute environment to have a maximum number of vCPU or a minimum number of vCPU that you want at any given time. But generally speaking, most customers let Batch choose and spin up how many instances we need in order to run the workload in the queue. Once the jobs are processed in the queue and it's time for scheduling, the AWS Batch scheduler then evaluates the jobs in the queue, and we run those in your compute environment, right? And so those jobs, Batch will figure out the mix of jobs to place on which instances, right, in order to reduce cost for you and cost and overall instance lifetime. Once the jobs are finished running, the output gets written back, and usually, again, in the case of image transformation, it gets written back to an S3 bucket. Customers can express dependencies in a variety of ways, right? And those are managed by AWS Batch, right? So the example here, I'm giving you just a brief example of how you can have dependencies, right? So you submit all of these jobs at the same time. You don't need to worry about them once they're in the queue, right? Batch will maintain their life cycle. But in this example, we have job A, which is a setup job coming in. We then have 3 distinct steps, right, in terms of that are submitted as an array. Here you have arrays of 100 jobs each, right? We have a heavy network I/O step, a GPU intensive, and a memory intensive step, right? This is very common in a machine learning work case, right? And so what we have is that those 3 arrays are dependent on, well, first of all, the later 2 arrays are dependent on each other, but essentially the arrays are dependent on that setup job, that heavy network I/O. Once that job is spun up and succeeds, the heavy network I/O array begins to run, and then we have 2 arrays that are expressing end-to-end dependencies on each other, right? And what that means is, for example, in this case, C0 is running, B0 is running, and then after that, C0 can run, right? And B99 can run, and C99 can run, right? B, for example, 99 doesn't have to wait for B1 to finish before C99 can start running, right? So that kind of end-to-end dependency makes it very easy to run workloads at scale. After, for example, the memory intensive step is finished, the cleanup job and kind of the analysis jobs run. Ideally here, what's important to realize is that this is managed by Batch, but also we only spin up instances according to what you need, right? So when the heavy network I/O step is running, right, we run that process. You don't need to wait for, or you don't need to have the GPU instances, right, running at the same time as your heavy network I/O. We only spin up those instances when we need them. When that workload is done, we shut down the instances in order to save you costs, right? And so that kind of managed dependency graph is crucial for use cases like the ones that we'll talk about in a little bit. Right, Batch, and because of this, right, Batch is a natural fit for workflow managers like we're going to talk about, right? So we have not only dependency capabilities, but manage retries, right? Even if you're using the spot, Batch will manage that retry for you on a spot termination. Again, to talk a little bit more about, or to see a little bit more about how spot works with Batch, I encourage you to take a look around in some of the other AWS Batch videos that we have on the site. But again, right, we see things like Luigi, Airflow, Nextflow is a popular genomics workflow manager. Netflix recently released their machine learning workflow manager called Metaflow, and of course we're here to talk about Flight today. So that's given you an overview of how AWS Batch works. I'd like to introduce Ali Gale, product manager out of Lyft, to discuss Flight and how their product uses Amazon services and what its capabilities are. Thanks.
Hi, I'm Ali. I'm the product manager for Flight, which is a cloud-native machine learning and data processing platform built at Lyft and recently open sourced. So I'll be walking you through the motivations for Flight, including the types of problems it solves, and therefore the opportunities it can afford you, your team, and your company. So over the last several years at Lyft, we've learned how hard it can be to develop production quality, large-scale machine learning and data pipelines. And two of the main reasons is infrastructure, where even if you just want to build a single pipeline to solve a simple business use case, it involves a significant amount of infra wrangling. And this is time-consuming, it's esoteric, and often involves teams having to have a couple of engineers dedicated just to infrastructure management, which is redundant and therefore costly. But beyond this, actually solving real business use cases is rarely done in isolation. Increasingly, you'll have several really complex pipelines that are all interdependent with one another, which necessitates the need for collaboration and also a clear way to kind of view this complexity and manage it. Beyond this, we've noticed several trends. The first is which, in order to be a successful business or product in the modern world, you have to have a good handle on data. And this means being able to process data at scale, to transform it, and increasingly to apply machine learning to it. So though we often think of data and machine learning as separate spaces, they're really convergent. And this is because a lot of machine learning is actually data processing and kind of data wrangling. Also, we see this increasingly, this convergence in our tooling as well as even in the personnel. This becomes really apparent when you consider that machine learning is way more than just a model. So if we look at what it actually takes to build a machine learning pipeline, we often usually just think of the algorithm, the thing that's actually making decisions based on the data. But it's so much more than that. In order to actually stand up a machine learning pipeline, you have to collect data, transform it, clean it, process it. You have to set up serving infrastructure. You have to tune your machine resource usage and allocation. There's a lot of other challenges to it, and most of those challenges are in the data space. And then just to drive home the point about interdependency, I have a simple or abstracted example from Lyft here. And in reality, it's a lot more complex than it appears. Each of these boxes is basically an entire service that might consist of several complex pipelines. And to put some numbers to it, at Flight, we manage over 3,500 unique workflows at Lyft, amounting to over 1 million task executions per month. And so to provide an example, at Lyft, we might have our mapping team, and they might produce a bunch of data that then our estimated time of arrivals, or our ETA team, then uses to predict how long it'll actually take you to get from point A to point B in your ride. This ETA, of course, then affects your price. So the pricing team has to consume that data to output the final amount that you'll pay. But of course, they don't just only use the ETA. They use a bunch of other factors, like whether there's a toll on the road, or whether or not you might get a coupon to get a discount on your ride. And so all of these services end up being really interdependent. So there's a strong need to be able to collaborate across dependency lines and then also manage the complexity of the whole system. And so Flight sits at the intersection of data and machine learning to make this all easy. We make it easy to declare and orchestrate ML and data workflows, abstracting infrastructure so you don't have to deal with that burden. And then we also make it easy to collaborate and reuse workflows across companies. And so now I'm going to hand it over to Matt, who's going to kind of go through the technical details and also provide a demo.
Hi, my name's Matt Smith, and I'm an engineering lead on Flight. And I'm going to be providing a few technical details about how we make this all easy. And I think the best way to do that is to talk a little bit about the problems that Flight has solved at Lyft and how it's evolved over the years. 3 years ago when Flight first started, it was a small group within the ETA team. The ETA team is responsible for training our traffic models and other things that directly power the expected time of arrival between point A and point B in the app. And obviously this information is used by a lot of other teams to do pretty much most of what Lyft does. And this small group within the ETA team was tasked with maintaining the infrastructure for these models. And this turned out to be quite a large job that had 3 or 4 engineers devoted to it. And this was a hard enough job just for one team. You could just imagine what this would mean throughout the company for other teams like pricing and forecasting and dispatch. It becomes a lot of engineering waste. So we came up with this easy, small mission statement, which was to abstract the infrastructure from business logic. And that's a pretty small mission statement, but it has a lot of large implications. For ETA, it's pretty easy to manage one workflow, but it becomes very difficult when that one workflow needs to be replicated multiple times and parameterized. This could be a workflow that learns the traffic in a city. That model is going to be trained through the same pipeline replicated for each city in America. In addition, you might have different variations of that model that you want to A/B test against each other. And when you start using a lot of the orchestration engines that currently exist, that becomes very difficult to manage. You run into problems with data integrity where things will stomp on each other. It's very difficult to scale out the infrastructure such that you can run these large ad hoc backfills alongside your production workflows without affecting the SLAs that are needed in real time. The jobs are heterogeneous and are various shapes and sizes. It can be very hard to effectively pack those onto a cluster and do that cheaply. And it also becomes very difficult to manage things like rollbacks, where you might end up trampling the models that exist in production. So the first thing we did is we basically came up with this. And it looks pretty simple, and it's creating the abstraction of a task. And this will look very familiar to most programmers because it's really just a function. It takes some inputs of a certain type, it produces outputs of a certain type, and it has a configuration. In this case, in the upper right-hand corner, we're showing a Python function which is configured as a Spark task with some Spark configuration. This might specify the number of executors, the amount of memory, the amount of CPUs that are necessary to complete the job. It also specifies the inputs that need to be provided to that task, and it specifies the types of outputs that will be produced. And just this simple idea allows us to think of these jobs as single atomic units of work that can be composed into arbitrarily complex workflows. And this also allows us to then leverage different compute platforms for our own benefit. In this case, we use AWS Batch a lot, and we do that by compiling these things down to containers and just maintaining a spec and a protobuf and submitting those into an AWS Batch cluster. That gives us extremely elastic scale and allows us to leverage their scheduler to do things efficiently. A workflow is similar to a task in that it also has a strongly typed interface. It will compose all these tasks together, and it could also compose sub-workflows into a larger workflow. And as you can see, again, data is front and center. We pass inputs of the workflow directly into a task, and the outputs of tasks can be routed into downstream tasks. And finally, that can be used to produce an output that is linked with that execution and with those input parameters. So now you can replicate a workflow as many times as you want, and with different hyperparameters or other inputs, and track all of that in a seamless manner. It also makes it easy to have different schedules for different sets of parameters on those workflows. So you could imagine, for instance, that at Lyft, you might want to train a traffic model in some cities hourly, and in other cities that have very highly varying traffic, you would want to train those more often, perhaps every 5 minutes. By using this workflow that's parameterized, it's decoupled, and you could have different schedules on the same workflow for different inputs. And these are also versioned, and this allows you to pretty easily maintain an auditable history of everything that has ever existed in your production, and go back and analyze any errors or issues you might have seen. It also makes it easy in the case of a rollback where you can immediately bring up a past version of the pipeline and take over when things go wrong. So we provided all of that for the ETA team, and we had a lot of success with it. It really unlocked a lot of development speed. And at the time, Lyft was growing very rapidly. And so some other teams heard about us and they wanted to start using us. So suddenly, we also had to concern ourselves with multi-tenancy issues. One example would be we brought on a pricing team, which needs to retrain pricing models regularly all over the country. And it basically processes, a huge amount of data from the entire history of Lyft. So we introduced the concept of projects and domains. This allows you to logically group workflows and tasks that might span one or more repositories or one or more containers. This means different teams can have different dependencies and need not worry about conflicting with one another. This also provides a configuration partition that we can use when interacting with services like AWS Batch to ensure that they don't step on each other's toes. In other words, pricing, if they need to run a workflow that is going to span across 1,000 nodes, we can ensure that the ETA models that need to be trained every 10 minutes with high fidelity do not get trampled on. And we do this all through AWS Batch, where we simply configure different queues and compute environments for these projects and dump our work onto them, and they deal with it for us. Additionally, the aspect of having domains is very beneficial when you think about the continuous integration of these pipelines. You might have a development space where ad hoc runs can be done such that you can test at scale on large sets of data, even perhaps production data. You can then advance it into staging where you'll run smaller workflows less regularly, but use that to run some validations and ensure the integrity of your workflow. And finally, you can push it through to production where we guarantee SLAs, access to large amounts of compute, and that will be the place where you can produce the data that directly impacts the business. So that's how we kind of kept tenants separate. But there's also an aspect of sharing where at a team like Lyft, you'll have a lot of people solving similar problems. An example of that would be in mapping. Pretty much everything at Lyft depends on a map. And so we have one team that is able to define the best state-of-the-art solutions for computing these maps and overlaying layers on them that can be consumed by other teams. And it's, in a lot of workflow orchestration platforms, difficult to share those tasks. In Flight, we make it so you can share tasks and workflows between projects. That means if you run a pipeline that depends on a new version of a map that has not been created yet, you can simply add that task into your workflow, run it, the execution will be billed against your team, and you will get the best state-of-the-art version of the map that was created or that the logic was created for by the mapping team. So to give a brief example of this, you can see here we have a project A and project B, where project A has defined a workflow and a task. The workflow is named pipeline A, and the task is named my model. On the right-hand side, we have project B, which is going to have a composite pipeline, which pulls in the workflow from project A as well as the task from project A and weaves them together. You can see we use some of the SDK magic methods to find a specific version of that pipeline and task, and we put it together in this composite pipeline, which will run in project B's context and use project B's resources. So Flight's gone through a number of iterations over the years. However, we've settled on what we think is a pretty good architecture. It's a pretty canonical example of a distributed system architecture where we have a control plane, a user plane, and a data or execution plane. And we have a number of components that allow us to interact with this platform in a variety of ways. So everything in Flight derives from our IDL spec. So this is protobuf based, and from that we generate clients primarily in Python, but we also, since it is protobuf, it will generate into any language that we need. Golang for our backend services. Through these clients, you can register workflows, you can register tasks, you can execute those workflows, you can monitor those workflows, you can retrieve inputs and outputs for arbitrary executions, and that can be done with the CLI that's built on top of it. It can be done with the web console, and it can also be done programmatically from a service using either the Python SDK or just the raw client. Once you call that client, it goes to a central registration service. This registration service will maintain a history of all task and workflow versions that you have created and allow you to recall those at any time and submit them into our execution plane. And the execution plane is where things get particularly interesting. So we have Flight Propeller, which is kind of the brain of the system, which will receive one of these specifications for an execution. It'll look through the workflow, it'll see the individual tasks that need to be executed, it will route the inputs and outputs, it'll handle faults and retries if necessary, and it will send off the work to numerous compute providers. That could be something hosted in Kubernetes, it could be a third-party service like AWS Batch, it could be another third-party service like SageMaker, it could be Hive, it can be Spark hosted in Kubernetes or on Kubel. The options are relatively endless. And although that general architecture was pretty good, we decided we needed to take it a step further. And again, this is from the growth of Lyft, where, as Ali had mentioned, we have dozens of teams operating on us with thousands of workflows, and these workflows have gotten bigger and bigger. To the point that we were not able to host all of our compute on a single Kubernetes cluster. When we're running Spark jobs that number in the hundreds of nodes, and we're running many of those simultaneously, we ran into inherent limitations in Kubernetes that forced us to start sharding our work across multiple Kubernetes clusters. And so that is something that is now supported out of the box on Flight, that we can submit to multiple clusters. This is also highly beneficial in a enterprise like Lyft, where we need to rapidly evolve this pipeline or this platform and the configurations on it, and we want to do so without impacting our production workflow system. So by using multiple clusters, they can be configured such that there are canary clusters where we can stage changes and see how the new configurations or new components work against real production or real workloads prior to rolling those out to production. This gives us high confidence in any change we make and allows us to maintain a high level of reliability. So one of the primary benefits of Flight is its serverless architecture. We are containerized. It means we can use AWS Batch. It means we can use Kubernetes. It means we can send work where we need it to go. We don't require users to worry about physical machines. They simply specify the amount of CPU, GPU, and memory, and we will make sure, either by submitting to Batch or to Kubernetes or some other compute fabric, we will ensure that those ephemeral resources become available. And it also makes it so that we are very elastic and we can automatically scale, and we can do this while being cost aware to be efficient with our use of resources. And we also offer custom rate limiting and resource pooling systems that can be used for certain services that might have slot limits. So an example of this would be a hard number on the number of Hive queries that can run at any given time. We can ensure that globally those slots are shared and that our tenants are able to accomplish what they need without being interrupted by others. Another aspect of the service-oriented aspect is that pretty much everything is done through gRPC and REST interfaces. There's no side-effectual behavior. There's no odd configurations. Everything can be done through the API, and this allows people to do pretty incredible things. One example at Lyft is we have a machine learning pipelines team that has used these clients to build a service where someone can use a GUI to drag and drop tasks into a workflow and see that scheduled in advance to production, which has really made it quite easy for anyone, whether they're a research scientist, a data engineer, or an engineer, to make the workflows that can be run at scale. So, in addition to the benefits we get from being input and output aware in terms of being able to deconstruct our workflows into these atomic units called tasks, we can also take advantage of that data for other things. And one example is Data Catalog, which is a service which is aware of the flight input and output specs that also provides memoization. Now, I think most engineers will agree with me that there has been a time where the way they debug something was by running something, realizing it failed, adding a print line or changing one line, running it again, and then seeing what happens. And usually it's still broken after you've done that. The problem with that when you go into workflows is that you might be rerunning steps that cost tens of thousands of dollars to run. That's not a good thing to do when you're running a business. So, because Flight is aware of the inputs and outputs to a task, as well as the version of the task, which includes the code, it can be specified by the user that the code is deterministic and that we should enable caching. That means that when Flight sees a task that is going to be executed, we can evaluate those inputs and the configuration for that task and say, hey, I've computed that already and it was successful. Here is the output. We don't need to spend $10,000. So that has really sped, and not only does that save money, it saves time. So another aspect of Flight is, we do manage workflows, or we do manage the execution of workflows for dozens of teams who have very high demands of reliability. And they also need significant observability into our workflows to ensure that they are achieving those reliability goals. So Flight has been built with extensive user visibility. We go drilling down per workflow, per task, per project, per domain. Additionally, we are highly monitored so that we can see the latencies in our system and ensure that we're conforming to the demands of our customers. Additionally, we have notifications that can be added to workflows, and these integrations include PagerDuty, Slack, and email so that on-calls can be notified in the case of a workflow failure so they can take corrective action. Additionally, in any large enterprise, data security is of great importance. So we have integrated with RBAC using service accounts or KIM on AWS, and recently have added OAuth authorization to ensure that people have access only to Flight when they should, and we'll be building on that to ensure apply additional access controls that ensure that people only have access to the specific workflows and executions that they should. So that's all well and good that we have a platform that's pretty reliable and scalable. But a platform is really only valuable if you can accomplish what you need to do on it. And especially in the space of data and machine learning, where there's a huge amount of development, it is very necessary to be agile. We want to be able to adopt whatever is the industry best as quickly as possible and make that available to our users. If we can't do that, no one's going to use us regardless of whether or not we are reliable or scalable. So Flight has been designed with extensibility in mind, and we have a rich plugin model. In this example, I'm going to show kind of the simplest plugin, which is an extension of the Python SDK to create a sensor task. This sensor task would be a simple object or decorator defined in a Python library, which can be imported by any user of Flight, which will enforce this behavior where if you return a sensor object, that the plugin will in the background pull on a Hive partition, maybe an S3 path, until data becomes available. And this is very simple. It will allow really rapidly extending the capabilities of Flight without making significant backend changes. However, that can sometimes not be enough. You can imagine the case where you have thousands of these partition sensors running at once, and it becomes kind of untenable to have 1,000 containers sitting around waiting. So we have also added the ability to add backend plugins. These plug in directly with Flight Propeller, which again is kind of the brain of our execution plane. And these you can plug in the logic that can send work off to different things. So again, AWS Batch is accessed via one of these plugins, as is SageMaker, Spark, Hive queries, Presto queries. All of these things can be managed or created through these plugins. And what you get out of this is you can provide a special visualization that will show up directly in our UI. You can add extra logs, and you can manage the lifecycle of these jobs from a stateful service. So now I'll go into a simple demo showing some of these capabilities. So let's begin the demo. What I'm going to be showing is a workflow that was created as a hackathon project by one of our engineers named Cheng Hong. And I think it's important that I mention that this is not actually something that's used in Lyft's business. It was an idea he had for a hackathon that I thought was pretty cool and makes a good use of Flight. So basically what his workflow is going to do is it's going to take a set of images that he had taken of his car. And what he is going to try to determine is if he had left something behind in the back seat. So if you had ever left a phone in the back of a car as your Lyft driver drove off, you might have wished that something like this existed. So the first thing he's going to do is he's going to write a workflow which will which will clean the image data and prepare it for training of a model. After that, he will validate it, and then we will show the results of this workflow. So here we have kind of this orchestrator workflow, which has these inputs. You can see some of them are required. They have different types. We have one that's a simple string, one that's a list of string. We have another which is a generic input, which is going to have a default, which is just some JSON loaded from a file. And we have a validation data ratio. These are this all probably looks very familiar to anyone who's written a machine learning pipeline. He's then going to introduce a data prep step into his workflow here, and you can see he passes some of the inputs to the workflow directly into that task. The next step is the training, and he's going to take some of the outputs from prepare and set those as inputs to the train method. And this will keep going through evaluation before finally we create outputs, which includes a model, which is a blob object that's going to be backed in S3, as well as some ground truths and predictions, which will be made available in the UI and through our APIs. So this is all done through the Python SDK, and it's pretty easy to do and develop this way. We have additional methods that make it easy to call upon our service to register those pipelines. So we have call register here, and we have gotten a ID for that registration. Our next step is going to be to actually execute that workflow. So here you can see there's an additional magic method on the orchestrator object, which will allow us to launch with inputs that we specify as just a basic dictionary of Python objects. That pipeline will be executed in our Flight KubeCon demo 2019 project and in our development domain. From there, we can wait for the completion, again using the SDK. We can see how many outputs were produced. There were 4. We can then download the generated model using the SDK's extensible type system that is aware of these object types and applies special behavior to them, and make that available and save it to a local file. And that will be then, in this case, we're loading a confusion matrix which describes the performance of that model. And we can see that here. Additionally, scrolling down, we can show that having loaded the model from an execution that had happened already, that we can render it against some test images and see its performance. Here's the back of Chang Hong's car, and you can see in most cases he did correctly identify when he had left something in his back seat. Now, I'd also like to show a little bit of our web console, and here you can see the page for a workflow execution. This is the same workflow that I just showed, and you can see the separate steps. You can see we have a prepare workflow that feeds into a download video task that then extracts frames from the videos and then corrects for luminance. Those outputs were then routed into this train method, which will rearrange the data into training and test and validation data sets, and then actually run a train task. And then finally, we'll have an evaluate workflow, which has a task to fetch the model, again rearrange some data, evaluate on the data sets, analyze, and predict. And what comes with all these is a nice set of logs, as well as inputs that are shown in the UI. In this case, there's a lot of inputs, and outputs. Again, lots of them. As well as the task definition that you can look at to be sure that you ran the right one and nothing crazy happened. So you might notice that these jobs only took 29 seconds or 1 second to run. This is an example of the usage of our memoization and data catalog. For the purposes of this demo, I didn't run a workflow that took hours and hours to run. I ran a cache version of it, and it quickly ran through, evaluated everything, saw that I had already run this, and merely returned the outputs. So again, some power there with the memoization. Okay, and that's it for the demo. So there's a lot of things coming up in Flight that we're pretty excited for. I think we've so far solved a good portion of problems for managing kind of pipelines in isolation, but we're starting to look into the bigger picture of these pipeline management. This can include reactive workflows, so workflows that react to specific events. This could be data landing in S3 or a Hive partition. It could be in response to actions by some of our agents in different tools. We're going to be doing a lot more work on data catalog to keep our data even better organized. We want to make it very easy to find and analyze the behavior of workflows across multiple versions and see what that does in terms of the data it produces. We want to make that very auditable so that we can understand exactly why things happened in the past in our business and correct things going forward. And again, we're recently open source, so we hope you join us on flight.org, join our Slack channel, take a look at our docs, and stay in touch. Thank you.